two masses and a spring. A pellet with a mass of 5 grams, so over here, strikes and embeds in a wooden block with a mass of 1 kilogram that rests on a frictionless horizontal surface and is attached to a spring. After the collision, the spring compresses by 14 centimeters. The spring obeys Hooke's law, so what does that mean? Well, that means that F equals minus kx, and the potential energy of the spring is going to be 1/2 kx squared. And we have some things we want to find. The velocity of the pellet block system after the collision, the velocity of the pellet before the collision. We want to find the change in total mechanical energy due to the collision, and find the period of oscillation of the pellet block spring system. Find the velocity of the pellet block system after the collision. Let's do a little notation here. Little m, capital M, denotes the pellet block system. Now, we're not given what V0 is. So because of that, we have to work this problem backwards. We're going to start off with the conservation of total mechanical energy as the pellet block system kinetic energy. Right, when the pellet hits here, it's going to start moving in that direction. It has a kinetic energy. That will turn into elastic potential energy when the spring is fully compressed. So we have our kinetic energy of the bullet block system. The pellet is already inside the block, and that will transfer into 1/2 k delta x squared. Here's what we have from the previous slide. We'll rearrange the equation to solve for the velocity of the pellet block system, input our numbers from the givens, and we find out that this takes off with an initial velocity of 2.79 meters per second right after the collision. Now we can use the conservation of momentum at impact to find V0. So we have little m V0 because it's just the speed of the pellet. The block is not moving at that point, it's just stationary. And then that will equal the sum of the masses as the pellet gets embedded in the block times the velocity of the system that we found on the previous slide. Divide through by little m, you get this expression, substitute in our numbers, and this is what we found from the previous work from part A. And we find the initial speed of the pellet is 561 meters per second, which probably is a little unrealistic because that's about 1,200 miles per hour. So that is one fast pellet. What is the change in the total mechanical energy due to the collision? Now be careful how this is worded. You certainly have a kinetic energy here from the pellet moving, and then when it strikes, just due to the collision, we want to look and see what the velocity of the pellet block system is. And of course, after that, it will compress the spring, which will change the potential energy. But we want it just due to the collision itself. So the only change will be the kinetic energy. And here's our final. Right? It's the initial velocity of the pellet mass system as it starts taking off. And obviously that velocity will keep changing as it compresses the spring. It will start slowing down. But once again, we're just interested at the change right at impact. So it'll be your initial velocity of the pellet block system times the double mass here, little pellet plus the big block, minus your initial kinetic energy of the pellet moving at that higher speed. You substitute in your numbers, and you find that you lost 783 joules of kinetic energy, of total mechanical energy at the collision. Find the period of oscillation of the pellet block spring system. We were told early on that the spring obeys Hooke's law, F equals minus kx. So we have simple harmonic motion here, and we use the period equation for that, which is T is equal to 2 pi the mass of the system divided by k. So our mass is the combined pellet plus block. Here's k. We carry out the math, and we find the period of the system is 0.315 seconds.